All right, folks, here we go. Lesson 1.2. I'm going to present a problem in this lesson. We're going to talk a little bit about scientific notation, and then we're going to really dive into exponential relationships here. Okay. So let's see. Our focus question for this lesson is, how are the chessboard and ballot cutting situations similar? And then how are they different? All right, so in this problem, we're going to take a look at a chessboard, and then we're going to compare it to the ballot cutting situation that we just talked about. Okay, but first we have some vocabulary to talk about, specifically regarding exponents. Okay, so we have something called a base, and a base it's just the number that you raise to an exponential expression, or that you raise to another number. So the number that you raise to an exponential expression. And the reason why I say exponential expression is because you can definitely have more than just numbers in as an exponent, right? You can have many things considered to be an exponent. So that's why we just say an exponential expression. Okay. If you take a look a little further down, right, this too is your base, right? It is being raised by an exponent. Okay. And now let's talk about the exponent. Well, the exponent is the in simple terms, it's the small raised number, right? It's always up and to the right of another number. Small raised number. And what does this do? It tells us how many times a certain factor is used. So the small raised number that tells us, or that tells how many times a factor is used. And I like to use the word factor because that tells you what type of math is happening. Okay, how many times a factor is used. Okay, now we have something that we called exponential form. And we actually did a bunch of this in the previous video here. Right, we were writing things in exponential form. We wrote the amount of ballots that were made after certain cuts by writing them in expanded form, right? Like all of those 2's, 2 times 2 times 2 times 2. And then the exponential form was just it's just a quantity expressed as a number raised to a certain power. So an example, 4 to the 5th power. This is what we call exponential form. It has an exponent in it, so therefore it's exponential form. All right, scientific notation is what we're going to take a look at in a second. But scientific notation is, think about it as, it's a short way to write either really, really big numbers or really, really small numbers. So really big or small numbers. And we'll take a look at that in a second, okay? And then lastly, we have this thing called standard form. And standard form, well, standard means, it's very common. It's probably the most common way. So standard form, we say, is the most common way the most common way used to express quantities. There we go. So the most common way to express numbers, or to express things. All right. So here, if you look below, we have some pictures to help you guys label things, right? So our exponent is here. Here's our exponent, 3. Then we call this exponential form, 2 to the 5th power, and so on and so forth. Okay. All right, but I want to talk about this thing called scientific notation. Okay. I don't know if you guys have ever messed around with your calculator and you got a super big number and your calculator did something weird and it would say 3.246 times 10 to the 32nd power or something like that. I don't know if you guys have seen that on your calculator, but that is exactly what scientific notation is. Okay. It is a way for us to write really big numbers like this, like this, or really small numbers like this in a better way that's a little bit easier on the eyes. Okay? So what you guys are going to be able to do is you're going to be able to take a number in what we call standard form and change it to scientific notation. You're also going to be able to do the opposite. You're going to take numbers in scientific notation and then change them back to standard form. Okay? If you guys notice here, it says the product is a standard form. So when we actually compute the exponents and we do the math, that's what we call standard form. Okay? So take a look. First thing you're going to do is you're going to locate the decimal on this number. In this case, I have 38,000, and the decimal is always to the right of whole numbers. Okay? Now, what you want to do is you want to move the decimal. You're going to move the decimal to the left until you have one digit to the left of the decimal. So take a look. I move it once, twice, 3 times, 4 times. It takes me four times to move the decimal so that one digit is to the left of the decimal. So what I do now is I rewrite this as 3.8. That is my new decimal. Okay, and because I moved that a certain amount of times, I'm going to multiply that by 10, and I'm going to raise that 10 to a certain power. And maybe you guessed it, but it's going to be 10 to the 4th power because I moved my decimal over 4 times. And now I have this lovely scientific notation, 3.8 times 10 to the 4th power. Let's try it again. So first thing, locate the decimal on the number. It's right there. Okay, now you're going to move the decimal to the left. With a whole number, you're going to move the decimal to the left until you have one digit to the left of the decimal. So that's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And so what we're going to do is, because there are very unique numbers in this number, we actually have to include all of them. So 1.099511.6. Once you just hit a bunch of zeros, then you can stop. Now, you multiply by 10, right? That's the whole idea of scientific notation. It's always multiplied by 10 raised to a certain power. How many times did I move my decimal to the left? It is 10 times. So we have 1.099511.6 times 10 to the 10th power. And there we have our scientific notation. All right. I was gonna say pause the video for a second to work on it, but I need to do one more example of we're gonna do this one, 0.00992. Okay. First thing, you're gonna locate the decimal. The decimal's right here. This time it's to the left. Instead of the right side. So what we're gonna do, you'll also notice that this number is pretty small. So what we're gonna do is we're gonna move the decimal in the opposite direction. We're gonna move it to the right. And the goal is the same. We're trying to move the decimal so that there's one digit to the left of the decimal. So there I go. So I move it 1, 2, 3 times. So my decimal is this 9.92. And take a look at this. I moved my decimal to the right. This time, my exponent is going to be negative. How many times did I move it? 3 times. So I say this is 9.92 times 10 to the negative third power. Okay. So moving your decimal to the right makes your exponent negative. Moving your decimal to the left makes it a positive exponent. Okay? So what I would like you guys to do is go ahead and pause the video and finish these last 3 here. Okay, the last one's a little, the 3.8, I want to see what you guys come up with. So go ahead and pause the video, work together if you need to, and then we will, I'll walk you guys through it afterwards, all right? Okay, hopefully you pause the video. All right, first thing, find the decimal. Now we're going to move the decimal until there's one number to the left of it. So 1, 2, 3, 4, 5, 6, 7. And I'm going to write my numbers here, 8.213. And then because it's scientific notation, I multiply it by 10 and I raise it to the number of times I move my decimal, which is 7. So 8.213 times 10 to the 7th power. All right, here we go. Next one, 0.000815396. Find the decimal. It's to the left now, so that means I'm moving my decimal to the right. How many times? 1, 2, 3, and 4. So my new decimal looks like this, 8.15396 times 10, and because I'm moving to the right, my exponent is negative, and I moved it 4 times, so it's negative 4. All right, here we go. Locate the decimal. I already have 1 digit to the left, so do I really need to move it at all? No, I don't. So really, writing this in scientific notation is actually longer than writing just 3.8 times 10, and we say to the 0th power because we didn't move it at all. We didn't move the decimal. We moved it 0 times. Okay. Now let's take a look at moving backwards from scientific notation. Okay. So take a look at the first one, 1.4 times 10 to the negative 3. So what I like to do is I like to start out with writing the number. So 1.4 times 10 to the negative 3rd power. If I were there, I would ask you, well, which way are we moving? Are we moving left? Are we moving right? All right, which way should I move the decimal? Well, if you think about converting into scientific notation, we already said that moving to the right, moving the decimal to the right, gives you a negative exponent. In this case, I have a negative 3 as my exponent. So to go backwards, I should probably go to the left. So I'm going to move my decimal 1, 2, 3. Fill in my spaces. My number is 0.0014. And there we go. Let's try the next one. In this case, I have 7.62. And I'm multiplying it by 10 to the 5th power. So notice how my exponent is positive, which means that if I were doing the problem, if I were converting from standard form to scientific notation, I'd be moving my decimal to the left, right, originally. So to go backwards, I'm going to move my decimal to the right. So 1 time, 2 times, 3 times, 4 times, and 5 times. So plug in your zeros. So my answer is 762,000. 7.62 times 10 to the 5th is the same thing as 762,000. All right, try the next two on your own, please. Pause the video, and then I'll walk you through it afterwards. All right, so hopefully you pause the video. Here I have my number, 4.634, and I'm moving my decimal back to the right. So 1, 2, 3, and 4. There we go. It looks like my number is 46,340. All right, and then the last one, 4 times 10 to the 0. Well, 10 to the 0 is the same thing as 1, so 4 times 1 is just 4. And there you have it, some scientific notation. Hopefully you guys are feeling okay with that. If you're not, please come and see me. I'll gladly walk you guys through some problems, and we can talk about how this works or what exactly it is, okay? But let us keep going on. And this is our problem. It's gonna last for quite a few lessons, okay? So let's read through this a little bit. So it says, one day in the ancient kingdom of Monterrey, a peasant saved the life of the king's daughter. The king was so grateful, he told the peasant she could have any reward she desired. The peasant, who also just happened to be the kingdom's chess champion, made an unusual request. So this is titled Plan 1, the Peasant's Plan. So the peasant says, I would like you to place 1 ruba on the first square of my chessboard. See, here's the chessboard problem now. Okay, so I would like you to place 1 ruba on the first square of my chessboard, 2 rubas on the second square, 4 on the third square, 8 on the fourth square, and so on. Continue this pattern until you have covered all 64 squares. Each square should have twice as many rubas as the previous square. Doesn't that sound familiar, you guys? All right. The king replied, Rubas are the least valuable coin in the kingdom. Surely you can think of a better reward. But the peasant insisted, so the king agreed to her request. Okay, so they gave us quite a bit of information here. So what they want us to do is they want us to make a table showing the number of rubas the king will place on the squares 1 through 10 of the chessboard. So let's take a look at that. So, hey, look at that. I gave you guys the first 2 already. So on square number 1, we have 1 ruba. And really the calculation for this is just 1, right? We can't really do anything to that. I'm going to leave exponential form alone for a second. Okay? Then, on square number 2, we place 2 rubas. So my calculation becomes just a 2. And in exponential form, well, how do you write 2? Well, that's just 2 to the first power. See what I'm doing here? Anyone catch it yet? Okay, on the third square, how many rubas should we have? We should have 4 rubas, right? The relationship is that it's doubling every single time. So the calculation would just be 2 times 2, or 2 squared. Now, can I go back to this first exponential form here? What would I write here? Think about it for a second. How could you rewrite it with the base of 2? How could you write an exponential form that equals 1 with a base of 2? Hopefully you said 2 to the 0th power, because anything raised to the 0th power is 1. All right. What I would like you to do is go ahead and fill in the rest of this table, please. And then I would also like you to add this n here. Okay, and see if you can come up with a pattern or an equation that represents this pattern. Okay, so go ahead, pause the video, work together if you need to, and then we'll walk through it afterwards. All right, so hopefully you pause the video. We're going to go ahead and fill in our number of rubas here. So every single time we move up a square, we get doubled. So that's 16, that's 32, 64, 128, 256, and then 512. And we are writing this in terms of 2's, right? Because we are doubling. I wonder what predictions you guys will have about a growth factor. 4, 5, and 6. 1, 2, 3, 4, 5, 6, and 7. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8, 9. And then let's fill in our expanded forms. That's 2 to the third, 2 to the fourth, 2 to the fifth, 2 to the sixth, 2 to the seventh, 2 to the eighth power, and 2 to the ninth. When you guys are writing your exponents, I ask that you be very, very careful. Please make the exponent smaller than your base, and make sure it's up and to the right, because if you write something like this, I'm gonna think it's a 25, okay? Please make sure you actually try to make it an exponent, okay? So that way I don't get confused, and then we avoid some confusion, okay? Well, let's talk about n. N represents any square number. So what equation could we possibly write that represents this pattern? Now, to give you guys a hint, think about your exponents, right, in exponential form, and how do they relate to our independent variable in this case, which would be our square number. So take a look. How does 2 to the 0 relate to 1? How does 2 to the first power relate to 2? How does 2 to the second power relate to 3? 2 to the third power relate to 4? So on and so forth. Hopefully you guys came up with this 2 not to the nth power, because the square number does not match the exponent in our exponential form. In fact, it's always 1 less. So our equation is going to look like this instead. 2 to the n minus 1 power. And there we go. All right. I have another table for you guys. And this table is going to represent the same problem, except this time we're going to be starting at 0. We're going to go back 1 step in the pattern. Okay, so there's this square number 0, okay, and following this pattern of the Rubas doubling every single time, right? If we know that on square number 1 we have 1, so to go backwards we should probably take half of 1. So that's where they got this 1/2 from. So on square number 0, the peasant's going to get half of a ruba, okay? And the calculation, of course, is just 1/2. Okay, next we have square number 1, and the number of rubas we have is 1. This time with my calculation, I am going to include this 1/2 here. So I'm going to take 1/2, and I'm going to multiply it. What could I multiply it by in order to get this number? Well, 1/2 times 2 gives me 1. Okay, I'm going to save exponential form for a little bit later, okay? Let's walk through the next one. On the second square, we should have 2 squares. So this looks like 1/2 times 2, right? 1/2 times 2 we know is 1, but we need to multiply that by 2 again, so that way we get 2 rubas. You guys see a pattern here? I'll do one more before I let you guys work on your own. There should be 4 rubas on the third square. So if I do 1/2 times 2 times 2, I know that's 2, but I need to multiply by another 2. There we go. Okay, go ahead and fill in these 2 boxes, please. Pause the video, fill them in real quick. We'll talk about it. Okay. Hopefully you pause the video. We know that on the 4th square there should be 8, and then on the 5th square there should be 16. Following the same pattern, you're going to take 1/2 times 2 times 2 times 2, but then times an additional 2. And then for 16, we're at 1/2 times 2 times 2 times 2 times 2, and then times an additional 2. Now let's talk about this exponential form. So really we could say this is 1/2 times 1 at the very top. So what I'm going to do for exponential forms, I'm going to say, well, 1/2 times, and remember that we're doubling every time still. So we still need that 2 as our base. And how do I rewrite 2 as, how do I rewrite 1 as an exponential expression with 2? Well, I just say 2 to the 0th power. So I get the same thing. I still get 1/2 times 1. Underneath, I'm going to take the 1/2 and I'm going to multiply it by only 1 2, so this is going to be multiplied by 2 to the first power. I'm going to take 1/2 again. How many 2's did I multiply by? I multiplied by 2, so 2 to the second power. Do you guys see a pattern here? 2 to the third. Then I have 1/2 times 2 to the fourth. And then I have 1/2 times 2 to the fifth power. So now let me ask you, what about n? For any square number, how would you, or what equation could you write to represent this? Think about that for a second. Talk with your neighbors, please. What equation could you write to represent this situation? All right. Hopefully you guys noticed that we took 1/2 every time. So I think 1/2 is good enough to be in our equation because it's there all the time. So it looks like I'm taking 1/2 and I'm multiplying it by something. Well, I noticed that I have all of these 2's here, right? So it looks like the 2 is also going to be a part of our equation. And then lastly, take a look at the exponents in the exponential form column. How do they relate? How do they relate to our square numbers? Do they match? Are they one less? In this case, they match. So the only thing we're missing is to the nth power. So here we have another equation that represents the same situation. Isn't that cool? I thought it was cool. Anyway, we're going to graph this now. So along the bottom, our independent variable is going to be our square number, right? The number of rubas depends on what square number we're on. So rubas is going to be on the left side. And let's go ahead and label this, we're going to go by 2's and skip every other line on the very bottom on the x-axis, 2, 4, 6, 8, and 10. And then along the y-axis, we're going to go up by 20's. So 20, skip a line, then 40, skip a line, then 60, skip a line, 80, and then 100. Okay, so now go ahead and graph your data, please. All right, so doing a quick sketch here. Our graph should start to look something. So at 7, we're at about 64. So maybe approximately right there. And then at 6, we're at like 32, which is about right there. 5, we're at 16, which is about right there. And then at the fourth square, we're at 8, which is underneath 10. And then eventually start evening out. And then on the 8th square, yeah, we're at 128, so we're definitely over. That should be a little bit higher. There we go. And then connect your dots as best as you can. Make a nice curve, a nice exponential curve. There we go. And we're going to write our two equations here. So we have r is equal to 2 to the n minus 1 power, right? Where r is the number of rubas. Two is still considered our growth factor, right? Because we are doubling, that 2 is very important. So we're doubling. Whoops. And then n, that represents your square number. There we go. All right, and then the other equation we came up with. So r is equal to 1/2 times 2 to the nth power. So the variables remain the same. The only thing that changed was this 1/2, and we'll say that this is our starting point. okay? This 2, it's still our growth factor. I'd like you guys to write it again, because yes, eventually we'll be learning about growth factors. So I think it's a good time to introduce you guys to it. So we're doubling. Okay. Now, these questions are all analyzing the problem here. So what I'm going to do is kind of like what I did in the last video. I'm going to have you guys pause for a second, figure out the problems that we're on, and then I'm going to continue with the video. Okay? So go ahead, work on question B, 1 and 2. Okay? Please explain in words. Please be specific. That's all I ask. Okay? And then answer the question thoroughly. So go ahead, pause the video, try your hand at B1 and 2. All right. So B1, it says, how does the number of rubas change from one square to the next? Well, that's pretty straightforward. So what's happening is, well, the number of rubas is doubling, right? Every square we move forward, the number of rubas doubles. So there we go. Okay, how does the pattern of change you observed in the table show up in the graph? And how does it show up in the equation? These lovely questions again. So we already talked about the number of rubas doubling. Okay, so that is our pattern of change. How does that pattern of change show up in this graph? So you guys might have said, well, in the graph, the y value, or the dependent variable, it just doubles each time, right? And you can see that on the graph. You can see that in the points you plotted. Okay, but how does this doubling show up in the equation? Well, if you were writing down what I was writing down as well, this is where your growth factor comes into play, right? The growth factor of 2 means you're doubling each time. And there you go. Okay. Now, same thing. Last question in this lesson. Last 3 questions, sorry. Last part in this lesson, I'll say. Okay, so pause the video, try your hands at question C, 1, 2, and 3. All right. Which square will have 2 to the 30th power rubas? And explain. So I think here it's important to remember your equations. So we said the equation, I'm just going to use the first one we came up with, 2 to the n minus 1 power. So automatically in my brain, I'm thinking, well, I know that r is equal to 2 to the 30th power. That's what they're presenting me with. So really, my square number should actually be 1 more than 30. So I think the 31st square, so I'll say that the 31st square will have 2 to the 30 rubas. And then I'll say, well, the exponent is always 1 less than the square number. So it's always 1 less than the square number. Boom, there we go. All right, what is the first square on which the king will place at least 1 million rubas? So here is a little bit of guessing and checking, or using your calculators, I'll say, making educated guesses. I know that the 10th square number is at 512, so it definitely has to be much larger. So messing around with my calculator, I think before I get into my findings here, remember the question's asking me for the square number, right? Not the exponent, but the square number. So I'm going to say that square 21 gives me at least 1 million, because when I use my equation, so 2 to the n minus 1, when I plug in 21, so 2 to the 21 minus 1, which is the same thing as 2 to the 20th power, I get 1,048,576 rubas. I can double check square 20. So if I do 20 minus 1, which is 2 to the 19th power, let me plug that into my calculator here. So 2 to the 19th power is equal to 524,288. So definitely not enough. So not the 20th square, but the 21st square. All right, Larissa uses a calculator to compute the number of rubas on a square. When is the first time the answer is displayed in scientific notation? So you guys definitely needed to mess around with your calculators on here. But I found that square 35 gives me my first scientific notation. So plugging this in, I do 2 to the 35th power minus 1 is equal to 2 to the 34th power, which is 1.717986918 times 10 to the 10 rubas. That is a lot of rubas, you guys. Okay, so hopefully you guys are enjoying exponential relationships so far. We have a lot more to get into later, but hopefully you're enjoying yourself so far. All right, with that, we are finished for today, and I will see you guys in the next lesson.